Hello, my name is Patrick McGonigal. I am a graduate student at Montana State University in the Land Resources and Environmental Sciences program. I also have my undergraduate in civil engineering from Montana State. I'm also a wildland firefighter with the U.S. Forest Service, and as it is June, most of the West is at risk of wildfire, and I'm currently completing smoke jumper training here in Missoula, Montana, in hopes to take the next step of my fire career and be a little more proactive by parachuting from aircraft into fires before they go large, being able to save a lot of these drainages, sensitive areas from the extreme effects of wildfire, especially in a changing climate. I apologize for not being able to give this talk to you in person. I will provide some contact information in the folder from which you've accessed the link to this YouTube video so that you can refer questions to me. I'll also reply to you as I'm able around my fire schedule in the summer. I usually work 14 days on and then 2 days off, so it might be a while before I get back to you, but I will do what I can. I'm currently a smoke jumper candidate, which means this is my 5th year in fire. I have 2 years on the hotshot crew and then 2 years on engine crews around Montana. I really like wildland fire. I've had more fun with it at the moment than civil engineering. Someday I'll be an actual civil engineer, but I haven't found a position that will work around this fire summer. And also, civil engineers tend to not use chainsaws for at least 10 or 15 hours a week, which I think might be a requirement for my future job. So it might be a little less large of an organization wherever I find myself, but I also like to be more proactive, and I like to be a boots on the ground type person. To make myself more hireable, I'm receiving this master's degree in land resources and environmental sciences, graduating in December. I hope that'll make me be able to design more with my civil background in a more ecologically cognizant way. I like fire because I see that it's an absolute shift in the status quo of wild lands. Most people don't experience nature to the point where a lot of these wild lands are just kind of a nebulous area that no one goes. It's the wild, it's the wilderness, and very few people are privileged enough to have the time and the resources to be able to get back in some of these places. But these places that seem static when there's a wildland fire going through, they become fantastically dynamic. And in reality, for the ecologically sensitive people, nature is always that dynamic and interconnected, but it's unfortunate that it seems to take a wildfire for the public and the perception around society to really understand how these natural cycles work and how dramatic the shifts may be when resources are ignored for the majority of that time, especially for management industries such as logging. However, our reaction to fire, it makes for good news stories and some crazy video, but our reaction to fire may not be as ecologically cognizant as it could be. Historically, this year is the 75th anniversary of Smokey the Bear, and historically the protocol for the smoke jumpers in the Forest Service was that when a fire was detected, it was out by 10 a.m. the next morning. That was a mandate. So 75 years of fire suppression has led in part to the extreme fire we see today, as well as the public perception that any smoke is bad smoke, and this kind of helps the idea of prescribed fire to be more difficult, less palatable than would otherwise we would like to see on the ecology side of things. But so people don't want their homes under threat, and they think that smoke and fire are scary, when usually we can work with them pretty well. But fire in the built environment requires a discussion of two variables: the risk assessment of that fire and the response to that fire. And as a civil engineer, it's been interesting to me to see how my studies have progressed from what I thought was a simple engineering problem, which is hill slope erosion after a forest fire. But this has led me to investigate a much larger picture. It's also an economics problem as much as an engineering problem, as much as an ecology problem. And the benefit of being an actual wildland firefighter, boots on the ground, is that I've been able to see how a lot of this work plays out as that change is happening. And those that have been there out on the fire line in some of these wildlands and worked some of these extremely difficult shifts, we start to get a little long-winded and soft-eyed when recalling these events. So I think there's a special recognition that to bear witness to such catastrophe, drama, or a natural process, depending on perspective, is a pretty rare allowance, and I'm certainly privileged to be able to take part in this. All right, continuing on. So fire response. There's a discussion here that revolves mostly around this idea of the emergency management continuum, which you'll be able to see on my poster here is an evolving matrix of variables that include the values at risk, your resources available, time is a very valuable resource, the values of the resources under threat, and the short and long-term goals of the management scenario. And the evolution of this continuum usually trends towards resource protection, and especially in the fire industry or fire realm, there's the glorified Hollywood at all costs emergency response that people seem to expect, but may not be the best case scenario, and it might put the first responders at risk. But when we're trying to keep things under control, it usually benefits us to be proactive and to set ourselves up for success. But how to do that is a very complex question, as a problem like erosion control eventually points to our social concept of an emergency. Erosion is a very slow process, but can have dramatic effects, much like the slow accumulation of fuel in a forest can have a dramatic effect of a severe forest fire. Our response to both those situations is different than if we'd been more proactive earlier on. Changing these outcomes requires delineation of variables we can control and those that we can't. So it turns into more of a risk assessment. My engineering brain sees erosion control as a simple study. You could find a certain variable, governing variable, everything's physical, but when you start relying on predictive services for, say, precipitation events that may lead to erosion on such and such slope of such and such angle on such and such aspect with such and such burn severity due to such and such fuels loading, well, you start adding a confidence interval, and then predictive services tend to not have as finite an answer as other civil engineering problems tend to. Then you throw in the subjective and relative idea of value at risk. If there's $1 million home on one side, if there's a community that has already experienced severe natural disaster and wants a full suppression strategy versus a fire use strategy, a community that could benefit from a prescribed fire but hasn't had that happen, and now there's a severe fire, well, you start relying more on social expectations than actual valid scientific fact. And again, this gets back to that 75th anniversary of Smokey the Bear. Fuel loading in our forests today due to Smokey is greater than ever and has been shown to lead to more frequent and severe wildfires. And returning to a natural burn cycle in all parts of the country, it's getting done much better now in the southeast and the southwest, but we require more public cognizance. As familiar as the public is with Smokey, we need to recognize the value of fire in our woodlands today. How do we do that? Well, the risk assessment of where we're at is a complex question. There's several key elements to fire. The basic fire triangle is heat, fuel, and oxygen, but for a wildfire, you already have the fire ignited. So you have fuel, you have conditions favorable to combustion, and the conditions favorable for spread of that fire. So usually in any part of the United States, these conditions are only met a few days each year. You would hear these as those red flag warning days of low relative humidity, high temperature, low fuel moisture, and sometimes high wind. Alignment of a fire with topography is hugely important. Natural fires tend to be lightning strikes which occur at the top of ridges where there's usually not much fuel, but human-caused fires tend to occur down the bottom of drainages where there's a lot of fuel, and fire likes to run uphill better than it does downhill, so that's where we find these extremely large fires. myself as a smoke jumper in the future, this summer, we'll be going to fires usually caused by lightning that are usually on a ridge top and usually in some area that nobody would otherwise go to because you can't drive to it, so we have to fly to it and fall out of the sky to it. But in terms of actual fire spread and risk to humans, usually this is around population centers. So alignment topography is super important. Dense fuel loading. People like to live near dense forests. They think it's nice and quaint, but this is also increases their risk of fire effects. And when there is dense fuel loading, the fires tend to burn more severely, which increases the effects or the potential for erosion for a single given precipitation event. Fire is a nexus of variables of varying return intervals. So how to define all these variables and when they line up to give, say, a heat map of fire risk is a difficult process. But we have several publicly available models out there. I will put the links in this folder. They'll be under the cited materials folder. But we have fire behavior and spread models, and these use anywhere from, I believe it's 6 to 42 different fuel definitions, and each of these inputs occurs at a different resolution based on certain flights and publicly available data over the West. Usually it's specific to the Rocky Mountain West. But we have fuel loading on 1 kilometer, 400 meter, and then in some cases 10 meter resolution. This is either by color, just basic variance in reflectivity, but it gives us the ability to define high fuel, high risk environments that have high risk of large fire spread should a fire occur there. And that allows the local agency to design fuels treatments, fire breaks, and any sort of other mitigation techniques to prevent large fire spread, especially towards population centers. Other fire models include Behave Plus, Landfire, Farsight, and Flam Map. And as you can see on the poster, on the bottom of that first page, these all lead to our predictive services capabilities. As far as techniques to control erosion as part of that reactive part of wildfire response, a lot of times on these large fires we have large heavy capacity helicopters, type 1 helicopters, including K-MAX heavy lift helicopters and Chinooks. And for a large incident, you usually have the funding to keep these helicopters on hand for days after your most severe fire activity. And in this time, we've seen benefit for hydroseeding, hydromulching, spreading of hay bales or millet or sterilized wheat grains, any sort of stabilizing structure to help decrease erosion potential in sensitive areas. And usually what I've seen and had the privilege to talk to people walking around the inside of these burns, usually they don't like to talk to us chainsaw artists because we're pretty dirty and smelly by 10 days into a fire. But like Trout Unlimited, Rocky Mountain Elk Foundation, a lot of these conservation organizations will provide matching funding for the home agency to provide these erosion controls above, say, a sensitive drainage that has a specific genetic trait in its cutthroat trout, or say it's an elk wintering ground, and we can't just have this whole slope slough off and go into the stream. So that funding during that critical crux, because as we saw in, for instance, last summer, the 416 fire above Durango, Colorado, burned its most severe burn period between July, I believe, is the 2nd and the 8th is when we were there. But on the 20th, they had an extreme precipitation event that ended up flushing extreme amounts of sediment into the Animas River down in Colorado, which you may remember is the acid mine drainage turned orange river from several years ago due to the Gold King mine spill. But that precipitation event in that burn scar released more metals than the mine spill that turned the Animas orange. So understanding the interplay between fire and erosion may allow us to better preserve some of these key areas. Large fire really only burns it severely intensely over about 7 to 15% of its area. And so even a 50,000 acre fire with a heavy lift helicopter spreading, a couple thousand acres of hydroseed and mulch at relatively cheap cost compared to hand seeding or the alternatives, which includes felling dead trees side slope such that they provide a roughness factor for sheet wash erosion, or other roughness element creation such as trenching, water bars across linear features, and seeding, hand seeding. These heavy lift helicopters are definitely one of the cheapest ways to go, but that requires cognizance on part of the management team during the time of the wildfire reaction to get some of these codes that you have to charge a lot of this funding towards done. And it may not seem as important as, say, putting out the smoke, which is what the public cares about. So again, it comes down to perception, which can be frustrating for the operators on the ground. And then the people that care about the water quality, they see the correlation between the smoke and dead fish. But just bridging that gap is, again, one of the greatest battles we face. I would again refer you to the cited materials I have in the folder at which you clicked on this video. They are provided by the Joint Fire Science Program, which is they conduct incredible studies across a variety of climates, ecotones, what have you, concerning fire and its effects across time and space. Their studies on rehabilitation after fire have been of great interest to me, specifically hill slope erosion control and road rehabilitation. And these sources, some of them I think are between 6 years and maybe 10 years old at this point, but they're constantly coming out with new stuff. It's all publicly available because these are government funded organizations, and I would encourage you to review these, as well as some of these fire predictive models. Some of them are pretty incredible, especially when you pair it with something like GeoWEP, the Geospatial Erosion Prediction Protocol, I believe is the acronym. But GeoWEP is extremely useful for dividing up any watershed provided by Google Earth or any like KMZ file. You can divide into subcatchments of different contributing area, and then you can further define roughness elements based on the already occurring fuel loading, vegetation aspect, rock fragment, percentage of exposed soil, everything you want. And it's been immensely helpful for me for routing precipitation events over parts of watersheds or entire watersheds through time and space, and then changing roughness elements and contributing factors on the soil side of things to erosion potential. And it doesn't quite get to mass wasting and debris flow dynamics, but that might be a more site-specific candidate for study. But highly recommend. Continuing on here, so we have the risk assessment side of fire. It's kind of a multivariate scenario because you have the predictive side and then the reactive side. So on the reactive side, we can see how hot the fire burned. Every night after a shift, we'll see a helicopter flying around with an infrared camera, and they'll kind of define the parts of the fire that burned extremely intense that day, because there'll still be some relic heat that camera can pick up. So you start to get a severity model or severity map of that fire, and when you align that burn severity with governing variables, usually its slope and aspect, and then proximity to a drainage, and also contributing slope area. Different models use different weighting factors on these contributing variables, but usually it's somewhere around a 60-meter slope of contiguous angle with no impedance by other roughness factors will contribute for your standard 10-minute storm intensity for your climate model. So it's all dependent on your particular climate model for the West to erosion. And depending on that 10-minute storm intensity, you can get different erosion effects such as sheet wash, or specific particle mobilization by rain splash, or the larger effects of mass wasting and rilling. Of course, timing is also huge, as well as coverage. It seems that in the first 5 years after fire is the most severe potential for erosion and erosion effects, but we've seen that in some cases, specifically the Hayman Fire of Colorado, erosion effects can occur much longer, and the city of Denver ended up spending, I believe it was $30 million. It's on the second page of that poster there. I can't have it up while I also record this video, but they to mitigate the erosion effects, which was nearly a quarter of which they spent to control the fire itself. So the economics of fire response is certainly a pertinent variable. Obviously, we want to protect personnel and property, but when we start talking multiple $1 billion of fire response for houses that may not equate to that value in their actual value, but yet we still have fatalities on these fires, it's hard to define a unit against which you can compare the value of proactive or prescribed erosion mitigation against reactive and kind of status quo, as we currently are, techniques. But this is a discussion I wish I could have in person, because these are where the questions you bring to the table usually cause us to branch off into a different element of the predictive services to fire or the solutions to the management continuum. Usually on evolving events, especially when I was on the hotshot crew, these are many tens of thousands of acres of fire that have burned, dozens of structures. By that point, people are running around chasing their tails, and we're purely in reaction mode. We have bulldozers going all over the place, cutting roads, saving houses, but also that dozer scar may last years. And we're getting pretty good at our rehab techniques. I specifically point to road rehabilitation techniques devised by the Rocky Mountain Research Station have shown pretty valid ways to reconstruct a road into the natural landscape and mitigate anything from like erosion specifics to invasive weeds and the view shed even of having a linear feature within a natural context. Overall, I'd say as I've given this talk under different circumstances, usually leads to discussion on the benefits of prescribed burning, which I think points to the social expectations of fire and the social construct of fire being a bad mechanism. But I also think we need to talk more, in addition to prescribed burning, about designing a context to fire and future fuel potentials, as well as the public acceptance of fire as part of the natural regime, such that our response isn't as dramatic and that we kind of plan for fire as we build. But this is a difficult procedure. I am, again, remiss to be absent to this great meeting here in beautiful Big Sky country, but this smoke jumper training has been a life goal of mine that I have spent many years working towards, and as I am in the last several jumps of our program here until smoke jumper graduation, I cannot miss the rest of this training. I don't have time in life to regret things, and I know my experiences from my future smoke jumping career will allow me to be a better civil engineer or hydrologist, soil scientist, what have you, later on in life. So if you could please look at my resume and contact information at the QR code that you see on the poster there. I will also attach a link here in the bio of this video. Please refer any questions you have to me, and I would love to answer them when and if I am able. Thanks.